what I would like to present today, it's an approach by transportation to random matrices. So several people ask me, okay, to use optimum transport, and we will see that we can't use optimum transport. I mean, at least I don't know how to use it. But in some sense, so I think optimum transport is what gives a bit of the insight first to this problem. So I will start to kind of go through optimum transport, explain some basic results in the theory, and then try to show you that I would like to use it, but I don't know how to use it, and then I have to switch. So, and that's the path. So let's start from optimum transportation. So optimum transport. So the optimum transport problem is basically the problem of transporting, let's say, two probability densities that I'm going to denote by f and g. So these are two functions such that the integral of f is equal to the integral of g is equal to 1. And the goal is to transport them so one to another in an optimal way. So first of all, what does it mean to transport? So to transport means that, so transport f onto g means that whenever you take a set A here, and you look how much mass g gives to the set A, this must equal the mass that f gives to the set t minus 1 of A. Okay, so T is a transport if the integral, by definition, if the integral of f over t minus 1 of A is equal to the integral of g over A for every set A. And in an equivalent way, this is equivalent to say that the integral of, let's say, any test function chi of t of x f of x dx must be equal to the integral of chi of y g of y dy. So these are two equivalent formulations. You can see that this implies this just by taking chi to be the indicator function of the set A, and vice versa, you just argue by approximation. If this is true for characteristic of function, this is true for some characteristic functions, convex combinations, and then you basically pass to the limit. So this is the definition of transport. And what does it mean to be optimal? So for optimality, so T optimal, what does it mean? So we have a cost function. It's some function which is given and says how much we pay to transport a point from x to y. So in my case, the cost function I want to choose is the quadratic cost, because usually this is very good for regularity theory. So cost, in my case, is going to be x minus y squared. So these are very natural cost functions. So once you decide that this is the cost you pay, then you see that to transport a point x to a point t of x, what you're going to pay is x minus t of x squared for one point. And then if you integrate this with respect to f of x dx, you get the total transportation cost. And then you simply minimize this among all the transport maps. Okay, so you take the family of maps which satisfy this constraint, and you minimize this. Okay.
So transport maps always exist?
In general, so if the densities are absolutely continuous, yes. If you want, there is a general theorem in measure theory which says that every probability space with no atoms is isomorphic to 0, 1 with Lebesgue measure. So you can always transport probability densities with no atoms with maps. So theorem 97, there exists a unique optimal T, and T is given by the gradient of phi, where phi is some function from Rn into R which is convex. Okay, so this is a theorem by Ambrini which says that the transport map not only exists, but it has a very particular structure. Is given by the gradient of a convex function. Yeah.
The admissible set, you fix the G.
F and G are fixed. Yeah, given F and G, there exists a unique. So, given F and G. Okay, so let me find. So this is the theorem, and now my goal is find an equation for T.
Do you make any assumptions on F and G or only probability measures?
Probability measures is enough. Okay, if you don't put any assumption at infinity, maybe the minimum is plus infinity, and then everything is a minimizer. But once that number is finite, then you always have So the Brenier didn't prove completely this result with no assumptions. The general statement as a writing here is due to mechanics, 95. Brenier put some moment
What
condition.
are the cost function not squared? Maybe L1 norm still chooses
If you put a norm,
not squared.
so if you put a different power,
Maybe
X, okay, yeah, any
L1.
power p greater or equal than 1,
Equal
you have existence. So if you want uniqueness, you need p greater than 1. If you put p equal 1, your existence, but you don't have uniqueness.
I see.
So it's a matter of strict convexity. This is strictly convex only when p is greater than 1. So there are, of course, several generalizations. You can put even more complicated cost, but for my purposes, this is the only one interesting. So I want to find an equation for T. So how do I find an equation for T? I start from that relation, the push forward. So I know that for every function T, the integral of T of x f of x dx is equal to the integral of Q of y g of y dy. And now this, assume now that y, so perform the change of variable, y equals T of x, and assume that T is a nice diffeomorphism for a second. Then you can just do change of variable, and then you get that this is equal to the integral of T of x, g of T of x, determinant of graph T of x dx. And now if you compare the first expression with the last one, and you observe that T is arbitrary, you deduce that determinant of grad T equal f over g composition T. So you have the equality between this guy and this guy. Okay, so this is an equation for T. And now, since T is the gradient of phi, we can plug this information inside and we get the determinant of the action of phi is equal to f over g composition grad phi, which gives us what is called Monge-Ampère equation. So this is an elliptic, degenerate elliptic equation. Is a bit like a fully nonlinear version of the Laplacian. The Laplacian is the trace of the action, and here we have the determinant of the action. We have a nonlinear function of the eigenvalues. Okay, so this is the equation we have for a transport map. And now the question is, what about regularity? Okay. So what about regularity? So we take the equation and we like to use regularity for Monge-Ampère to prove regularity. This is not so easy because these are degenerate equations, so you cannot just prove regularity as for the Laplacian by interior estimates. You cannot say Laplacian is smooth, then the function is smooth. You need to look at the whole geometry of the problem and the boundary conditions. So there is a classical result, well, when a classical result of Luis Caffarelli, I want to state in 96, we state the following. So assume that f and g are, so f is defined from omega into r, g, let's say, is defined from capital lambda into r, omega and lambda are smooth, uniformly convex domains, uniformly convex domains, and f and g are smooth and strictly positive. In omega and lambda. Then phi, in fact, t, if you want, from omega closure to lambda closure, is a smooth diffeomorphism. So the picture is like I have this omega, I have lambda, here I have my function g, here I have my density f. I mean, they could overlap, of course, the two domains. This density is strictly positive here and is smooth. Let's say it's infinity. Same thing for g. Then the transform map is a smooth diffeomorphism. Okay? So these are smooth uniform domains in a REM. These are general dimension. Okay, so this is by now relatively classical result in the theory. But why are we interested in this kind of results? Oops. So the reason is because we would like to use, so there are, several applications, but one potential reason for regularity is because we would like to use transport maps to perform change of variables. Let me make, applications to regularity. Of regularity. Example. Suppose G is a probability density, and we want to compute, for instance, its moments. So let's say the integral of yi, yj, g of y dy, whatever. I and j are two coordinates. Okay, like second moment. Okay, maybe computing this could be extremely complicated. So I could say, well, I use now the formula, the change of variable formula, which is here, to say, so now I take pick, so I pick f nice, so that I know how to compute. I know how to compute integrals. And standard example is the Gaussian. You take a Gaussian, you know how to compute every moment of a Gaussian. Okay, and then you apply optimal transport, and you discover that the integral of yi, yj, g of y dy is equal to the integral of tx I coordinate, tx y coordinate, f of x dx. Okay? And now maybe I have a nice expansion for t. Now let's say that I know how to expand it in some power series or something. So I have maybe some linear like a dot x plus a matrix bxx plus cxxx. So these are like products of possible combination of then I start to get some matrix some function aij ax a tensor aij plus some other expression. Actually, I shouldn't use it. M1 then M2 x, depending on 3 copies of x plus blah 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 times f. So basically, if I have some expansion for t, some properties of t, I can have a guess. I could try to plug in this expression and compute this quantity in terms of this quantity. Okay? So that would be an example. A more now, okay, this looks kind of stupid because a lot of time you don't need this, but it starts to be interesting, for instance, statistical mechanics, when you have a huge number of particles. So now this is dimension n, but n is huge. In particular, you would like to take maybe limits as n goes to infinity. Understand this as an asymptotic expansion when the dimension is going to infinity. Now the problem, so this is interesting. So interesting when n tends to infinity, but the issue is that regularity theory is bad as it depends on the dimension. So if you look at all the estimates basically for already for the Laplacian, but basically already also for this kind of motion pair stuff, I mean the estimates are dimension dependent on the regularity. So that's an issue. Okay, there is one case where, okay, there are a few cases, but let's say one model case where there is an estimate which is independent of the dimension. And this is due again to Scaffarelli in 2000. So what we proved, the theorem, 2000, he proved the following, that if f is of the form e to the minus v dx, and g is of the form e to the minus w dx, where v and w are uniformly convex, and C2, so you have that the Hessian of v and the Hessian of w are between, let's say, two constants, lambda identity and mu times identity, then T is by Lipschitz, and the Lipschitz constant, the by Lipschitz constant, depends only on lambda and mu, not the dimension n. Okay? So if you have very particular densities which look like Gaussians or perturbation of the Gaussian, so like e to the minus s square or whatever, then the map is by Lipschitz, and this estimate is dimension independent. So as an application, for instance, what Luis showed, for instance, that you can use this to obtain, for instance, log Sobolev inequalities. Basically, you could reprove some of classical theorems that tells you that for density like this, you have log Sobolev inequalities, and basically the Lipschitz constant there exactly gives you the right bound of the log Sobolev inequality. Okay, so this looks good. At least there is some case. But now I will move to my problem. So up to now I just talked about optimal transfer in general. Now let's see exactly the setting where I want to apply it, and we'll discover in a second that this is completely useless for me. So that's the problem. So application. So my problem. So as the title said, there were random matrices. So what is a random matrix? I take maybe, so I will do the case of symmetric matrices. There are also, you can do this also with complex coefficients. I will do symmetric real matrices. So I have a matrix A11, ANN, so we'll capital N is the dimension. Here I have coefficients Aij, Aji. I'm going to assume that Aij is equal to Aji, so the matrix and matrix, these are real. And I'm going to assume that Aij is randomly distributed. So this is a random coefficient, this random function, and it's distributed as, let me first do the simplest case. E to the minus n t squared over 2 dt. So on R. So this is like a Gaussian distribution. Let me just check the coefficient. So in one each coefficient, so you pick randomly each coefficient of your matrix with a Gaussian, according to a Gaussian density. And they put a capital here, which is the same as the number of rows or column, because that's the one which gives the right scale. It's just, it doesn't really matter, but if you want them to get some non-trivial limit, that's the coefficient you have to put, yeah.
They're independent.
Every coefficient is, yeah, all the coefficients are completely independent. So this is the simplest case. I mean, when people start to look at random matrices, that's basically the easiest you can consider. You consider the coefficients are distributed independently and according to a Gaussian law. And we consider symmetric matrices, yeah. Because in fact, what you're really interested in is not really the matrix itself, are the eigenvalues. And so now I have a now what do I have? I have that my coefficients are distributed according to some law, so independent Gaussian coefficients. But now my question is, okay, how are distributed the eigenvalues then? Right? I have random coefficients. I can try to look at the probability distribution of the eigenvalues. So this, at the moment, is a distribution of, here I have n plus 1 over 2 coefficients, right? Because I have all these upper triangular matrix. But I want now to go to the eigenvalues, n eigenvalues. Okay. So let me tell you what is the distribution. So in this particular case, the law of the eigenvalues is the following. So you have e to the minus, so the eigenvalues are, let's say, lambda I, is e to the minus sum over I of, with an n in front of lambda I squared over 2, d lambda I, so d lambda 1, d lambda n. This is the law in R capital N. But in fact, the eigenvalues, they're not independent. Because if the eigenvalues coincide, you have a problem when you try to diagonalize matrices. When you look at the way you diagonalize a matrix, it's in a sense everything is smooth as long as you have no eigenvalues coincide. But then when they start to coincide, you can have singularities. And you have, in a sense, this should be seen here. And in fact, the formula is that here you have a product from I less than j of the modulus of lambda I minus lambda j. And then you divide this by the integral of the same expression to make it a probability measure. So the eigenvalues are distributed in a Gaussian way, but with a weight in front which vanishes whenever the eigenvalues coincide. Okay, so this is the probability distribution. Okay, I'm going to consider a more general model. So this is like the standard model that people studied. And basically for Gaussian, there are tons of probabilistic methods to understand basically everything you want about eigenvalues. So people are pretty happy about Gaussian. But maybe you don't want to study just for Gaussian densities. Okay, you may want to understand what happens when you look at more complicated distributions. So here I will focus on a particular model, and then I will discuss at the very end some other extensions, where I will consider, so I'm going to define the following probability, P, let's say, n v of d lambda I. This is gonna be the product. Let's see. Let me take a bigger chalk. Product I less than j, lambda I minus lambda j, e to the minus n sum over I of v of lambda I. So I put a potential. A bit
Let me
like
ask you this question. The result you said before, is this a classical result in statistical mechanics, or is it
Which one?
something new? This thing with this energy. This is new. I mean, I wanted to know where the result went.
which
When
result?
was this result proved? This thing.
Well, I didn't state any result. I just said that if this is this, then this is this. That's a computation.
This is a result. The law of the eigenvalues is this.
Well, I mean, an exercise. That more than a theory.
And this is a classical result.
Yeah, that's the first thing. People started to study random matrix. They took this and they make the change. They compute the change of variable. And they discovered that this is.
I mean, pointing to this factor lambda I minus lambda j is like taking into account the problems of the boxes in the matrix when you do
Change of variable.
Jordan.
Yeah, that's a Van der Moor matrix. It's Van der Moor.
Oh, okay.
It's a determinant
So
of
this
a
is
Van der
classical
Moor.
result.
Yeah, I mean, that's like the starting point of the theory.
Okay.
People say, okay, this is the formula, we found it, now we want to understand this.
Okay.
There is nothing deep. Yeah,
Just to know what is the exercise.
yeah, this is no.
I don't see it. How is this positive in this density?
What do you mean?
I minus lambda j simply. No? There's
There's a
absolute
modulus.
value. There's absolute value.
Absolute value of lambda minus
Okay.
lambda j.
I
Yeah.
thought it can just-
Yeah. There's an absolute value here.
It's the lambda.
And then I have the d lambda 1, d lambda n, and then you normalize. Okay? So this is a bit something very natural in some sense, where instead of having a Gaussian distribution, you have a distribution according to some different potential. Okay?
An integral into numerator.
No. No, this is a measure. And below I just divide by the integral of the measures just to make it a probability. Okay, so now the goal, so the idea is the following. So before we had two densities, F and G. Look, for instance, Luis' result, right? He had e to the minus v, e to the minus w. You could prove that there is a nice change of variable between them. Now I would like to do something similar. I want to put v and w, so two potentials, understand, can I relate the distribution of eigenvalues using some change of variable? So instead of calling the potential w, it's more convenient for me to call it v plus w. I mean, it's the same. Just call it v plus w. So I'm going. So my goal. So goal relate some the p and v and p and v plus w for v and v plus w uniformly convex. Okay, so I take now again uniformly convex densities, uniformly convex potential. They're going to be much more than C2 later, we'll see. I take uniformly convex potential and I would like to understand what are the relations between the two densities. Now you see that Lewis' theorem is completely out of applications because if you try to write this as an exponential, you could do this, right? This is exponential minus sum I less than j of log lambda I minus lambda j. So you could put this as an exponential, but this is absolutely not convex. Actually, it's very singular. So we are completely out of that setting. And the proof does not generalize. So don't try to apply it, it doesn't work. Okay, so this is a very singular term, which creates a lot of problems.
So you wrote a product distribution for the eigenvalues, but does it have a corresponding product distribution for entries of the matrix?
No, so there is no obvious way back. It's not exactly just an obvious change of variable. These are, so the one I wrote are distribution for the entries which are invariant under the action of the orthogonal group. So every density like this is a density on the coefficients which is invariant under the action of the orthogonal groups because it's something defined intrinsically on the eigenvalues. So these are kind of particular distributions. But it's already a large group, and very often people, the already distribution are very often defined directly on kind of functions of the eigenvalues. That's how people even define. So if you even do functional calculus, if you want to define what is the matrix to the power 1/2, that's what you do, right? You always pass the eigenvalue. So it's a very natural set of random matrices. It's not everything. I mean, you cannot get every distribution here from a distribution there in this way, because these are just on the eigenvalue. So if the distribution here is not invariant under the action of ON, you're not going to get something on the eigenvalue. You cannot read it naturally on the eigenvalues. So I'm going to consider anyhow probabilities of this form, and now I would like to understand, can I relate the properties of two probabilities like this? So there are several issues, right? So I could try to say, okay, maybe still optimal transport work, but basically, so I can tell you we tried, and I have no clue how to do that, right? Because again, so there are two issues, right? On the one hand, Lewis result does not apply, the one in dimension, the one which is in infinite dimensional, and so you have at the same time the singularity of the log. But even if you try to do an estimate in finite dimension, I wouldn't even know how to do that, even in finite dimension, because there is again the log. So regularity for Monge pair is not obvious for an equation like that, even if you just consider the pure PD problem in a REN, because you have these products. Remember that the theorem of Lewis of f and g, the one in 96, he said f and g must be strictly positive. These are not strictly positive. Lambda I can be equal to lambda j in some points. So you have regions where the densities vanish, both f and g. So this creates problem at the PD level. Okay, so what was then our idea? Idea is we don't need optimum transport. Just transport. Why do I care that it's optimal? The change of variable formula that I explained at the beginning, I want to do a change of variable. Why do I care that it's an optimal map? So I just want a transport. I just want a map which sends f on g and maybe is sufficiently smooth to do the computation I need. Okay, now I have to find a transport which works for my problem. How can I get it? So optimal transport gives an intuition, because, so the idea is this. I want to go, let's say, from, let me just check the notation. Okay, so let me go, so define. So I want to go from that density, PNV to PNV plus T. So to go from one to another, I want to interpolate between them. So I'm going to interpolate by considering PNVT, where VT is just V plus TW, T between 0 and 1. So you just interpolate between the two potential in a convex way. Okay, this is the most innocent thing you can do. And now write PV, T, and T, N, as a function rho T of lambda times d lambda. Right? So the density, you have this density times the back measure. So these are my these are family of densities, which at time 0 is my density, the one I start with, time 1 is the one where I want to go. So here I have root 0, let's say here I have rho 1, and I have rho T in between. And I would like to find a transport from rho 0 to rho 1. How can I do this? Well, let me try to do it by steps. So the intuition was, okay, if I want to go from 0 to 1, I could do from 0 to epsilon, from epsilon to 2 epsilon, to epsilon 3 epsilon, and so on, 1 over epsilon times. Now, why epsilon is better? Well, okay, let me assume that, let's say from a time t, I want to go to rho t plus epsilon. Okay, from here to here, I have a way to go, which is optimal transport. I could do that, just for a very short time. So here I compose optimal transport. So I apply t, let's say t plus epsilon. So t plus epsilon is optimal transport from rho t to rho t plus epsilon. And this is, by Brenet theorem, the gradient of function phi t plus epsilon. It's the gradient of a convex function. So I have the gradient of a convex function which allows me to go from here to here. In addition, what is phi tt? Phi tt is the optimal transport from, so let's say grad phi tt is the optimal transport from the density to itself. So grad phi tt of lambda is the identity lambda, right?
Yes.
Because I don't move. So I would make the following answers. Grad phi t plus epsilon of lambda could be equal. So okay, I can write this as saying that phi t of lambda is modulus of lambda square over 2. And then let me try this way. So phi t of epsilon, I'm going to write it as lambda square over 2 plus epsilon psi t of lambda plus little over epsilon. So this is an answer. I don't know if this is true, but I can hope that this is true. Okay, I have an expansion for the potential. Okay, but then I can do the following. I can remind myself that this
So in that notation, let's go slowly. Lambda is space.
lambda is like the variable in Rn.
Yeah.
So lambda is the vector lambda 1, lambda capital N in.
Lambda should be eigenvalues.
Well, later is going to be the eigenvalues. Here we're thinking it as a variable, right?
Okay.
Doesn't matter what it represents. And sometimes these are the eigenvalues, but now you can just think of a probability density or
You are
something.
in fact working with the idea that this is the eigenvalue space.
Right.
You're working.
Now I am on the eigenvalue space, and I want,
Everything is done in the eigenvalue space.
Yeah.
Okay.
I will never, and you can even forget that these are eigenvalues if you want. I
Yeah.
just have a probability densities on
You
R
can-
capital N that I
in
want.
the end, it will be applied to eigenvalues.
Right. So remember that the determinant of the action of phi t plus epsilon, so this motion pair is equal to rho t plus epsilon of gradient of phi t plus epsilon. This was the equation we got for motion pair. It was what I wrote before, right? If you transport f onto g, then this is the formula. Now plug, so call this star, plug it in, apply star. So take this expression, plug it inside. Okay? So you have this equation and you linearize it basically. And you just plug in this expression, then plug it in sign, and then you're gonna let epsilon goes to 0. So what is here? This is gonna be the identity matrix plus epsilon, the action of psi t, plus little over epsilon. Then you take the determinant. And this is equal to 1 plus epsilon Laplacian of psi t plus little over epsilon. If you do the expansion, what is the determinant of identity plus epsilon gives you the Laplacian in the first order, just a computation. So then you do an expansion in epsilon here, and you equalize the first order terms. And I can tell you what is the formula is this following equation. So you get the following equation that I'm going to call L of t, because it's linear. Its Laplacian of psi t is a constant, so this is a constant, minus the sum I less than j of di psi t minus dj psi t lambda I minus lambda j. So this comes from the logarithm, when you differentiate the logarithm. Then you have plus n sum over I of w of lambda I, and plus n sum over I of v t prime of lambda I times di psi t. Remember that vt are all functions from R into R, because they're defined on R. That's right. I mean, the densities, right? Tn vt is product lambda I minus lambda j e to the minus n sum of v of lambda I b product of v lambda I. So these are functions on R.
So in your answers, what are these little epsilon? You don't care.
I don't care. Anyhow, let epsilon goes to 0.
Mhm.
At the end, what is the partial derivative of at the end of your equation?
Partial derivative with respect to I
Uh,
of psi t. The I of psi t. So this is what you get. Just plug in and you compute. Not a surprise. Okay, now suppose that I can solve it. So this is not a super nice equation because you have the Laplacian, but you have the drift term, the second one, which is kind of singular. And for the moment, let's forget it. Let's assume that I know how to solve that. And let me show you how you can get a transport map. So suppose we can solve LT. Now I want to construct a transport map. So what is the idea? The idea is that suppose that I know how to construct it up to time t. So suppose that I know already how to go from 0 to t. And I want to see how to go to t plus epsilon. So suppose I have a map ST sending rho 0 to rho 2. Then I will ST plus epsilon, I could set it to be what? T plus epsilon composition ST. Simply I go first with ST and then I compose with the map. But what is this? Okay, I canceled that, but okay. This was, so t plus epsilon is the gradient of this function. So this is identity plus epsilon grad psi t plus little of epsilon composition ST by these answers. Okay? So this is equal to ST plus epsilon grad psi t composition ST plus little of epsilon. Now take this on this side and divide by epsilon. I get that S t plus epsilon minus st over epsilon is equal to grad phi t composition st plus little of 1. But this is what? This is dt of st plus little of 1. So what is so what do I discover? That if I know how to solve it up to time t, I know how to solve it for a small time by solving an ordinary differential equation. I have a function st defined on my space, which shall solve st dot equal grad phi t. So basically, grad phi t is my vector field. I have a vector field in Rn. I can flow the vector field, and by flowing the vector field, I get a transport. So
up to errors that you have to take into account.
no, there is no error here.
There is no error in here.
Because then I let epsilon goes to 0. The error just comes from epsilon. But then when I let epsilon goes to 0, there is no error.
But then if epsilon goes to 0, you are not increasing your time.
Infinitesimally, yes, because I took t plus epsilon st divided by epsilon. So infinitesimally, I'm doing that. I'm certainly finding the infinitesimal evolution that I have to follow to propagate. So I get, now the strategy, idea, find psi t, and then solve the ODE, dt st equal grad phi t of st, S0 of lambda equal lambda. S1 is a transport. Basically by construction.
So basically you locally make it optimal, but globally it's not optimal.
Right. I just use this as a kind of intuition. So I use infinitesimally optimal transport maps to flow, but then I think once you put them together, there is no reason for them to be
So
optimal.
difficult is having good estimates on grad C, otherwise you cannot solve the equation. have row 1.
Right. Well, they say, yeah, exactly. The problem is, what is this?
Careful, yeah. You did something bad.
Live will return.
Okay.
It's even worse.
Yeah, because it was, I don't know.
As long as the backward goes up and down, we'll have to
Just
take care of it.
Yeah, just-
Right, yeah.
Sorry about that. Okay. Okay, so well, this looks promising. The only issue, so I'm gonna keep the equation here. The only issue that I have no clue how to make estimates for this equation. I have no clue. So I started from a problem I didn't know how to solve this. I don't know how to solve it. But there is a hope, because I don't really want to solve this equation. I'm interested, so we are interested to what happens as n goes to infinity. That's basically what people are interested in. It's for limit as the dimension goes to infinity. Okay, so this means that I have some kind of freedom in the sense that I can do the following. So, idea, solve LT up to an error epsilon n, where epsilon n goes to 0 as n goes to infinity. So I'm not going to solve that PDE. I'm going to almost solve it. I'm going to find an approximate solution of it with some error. Then you are still going to, so first step would be solve this PDE. Second step is define ST through DOD. And 3, we're going to show that S1 is a transport up to an error epsilon n. So what do I mean by this? The kind of estimate you can show whatever epsilon. I haven't been very precise on what is the error, but basically you will try to show this kind of estimate that actually this is what we can prove. The kind of estimate we get is something like if you take the total variation of S1, the image of the density row 0 to the map S1, so if you use S1 to send the map somewhere, and you do minus rho 1 in total variation, which is the sup over modulus of key less or equal than 1 of the integral of key S1 push forward rho 0 minus rho 1, that's the same. This is bounded by constant epsilon n. So we are not going to find exactly a solution. A transport is not 0, but it's close to 0. And in particular, this is going to tell me that maybe some properties are true asymptotically when n goes to infinity. Now, if your epsilon n is too weak, you're going to find only trivial results that no one cares. So you need some good dependence on n here. You cannot just get something little of 1. That's not enough. Actually, you have to go down at least, we have to go down below square root of n, 1 over square root of n. In fact, we get something like log n over, instead we get something around log n square root of n. Do you have square root of n? No. Okay, now for this one I don't remember, but I will. There are other estimates where you really need a dependence. Here, what do we get? It's been a while when I wrote this. Okay, yeah. Actually, this one we get is gonna be like log n square over square root of n, which is good for a lot of purposes. Okay, so why 1 is it better? So what is the advantage of 1? usually solving approximate PD is not obvious. But okay, one solving up to an error is better because I can make an ansatz again. In the sense that I can guess what my solution should be. The kind of answers we're gonna make is this. We're gonna say that psi of this is a function of eigenvalues, right? But I can start to guess what it will be. So basically, I have these two distributions of eigenvalues. Okay, one distributed according to one density and one according distributed to another density. I want to transport one to another. That's what is going on. I could think that basically what's happening. Okay, if the eigenvalues didn't interact, I would just send the first eigenvalue to an eigenvalue, the second value to an eigenvalue, and so on, eigenvalue by eigenvalue. So that's not completely stupid. So I could start to say that the first term is going to be some function psi naught of t of lambda I. So basically, this function is a sum of functions which depends only on one coordinate. Then I need corrections. This is not enough. This is going to be just the leading order term. I need corrections, and I'm going to put some new function, which is still depends only on eigenvalues, but is in order 1 over n. So the idea is that the eigenvalues are uncorrelated first, and then so this is like the level 0, and then an order 1 over n, okay, I still have a term of uncorrelation, but at order 1 over n, you expect the eigenvalue to start to interact a bit, right? The fact that they cross, there is but basically, I think that the fact that two eigenvalues interact is much more likely than the fact that three eigenvalues interact, because it means that they're all equal at the same time. It's like if you think in an equation like Boltzmann, people always say it's very likely that two particles interact, but not that three interact at the same time. That's what happens. Always you consider collision by two. These are the most likely events. So you expect that the fact that two eigenvalues interact is more likely. So then you say, okay, then I have a correction at second order, still at order 1 over n, lambda I, lambda j. Sorry, this is 1 over n squared, yeah. Yeah. Okay, maybe I should, okay, let me make it, let me normalize by 1 over n. It doesn't matter because then I divide by everything, but let me do it this way. So in this way, look, here I have 1 over n and a sum of capital N terms. So this is of order 1. So this is like, oh, 1. These are, I have n terms, 1 over n squared, 1 over n. N squared terms, because I have I and j, you can do maybe only I different from j. N cube, this is again order 1 over n. Order 1 over n, order 1. Okay? So this is, and then you could go on. I mean, you could start to put interaction in 1 over n squared. But we're going to stop here. Already it's a mess like this. So then you say, okay, this is my ansatz. I take this and plug it in the equation. Right? You compute the Laplacian of this, the Laplacian of this, the Laplacian of this. You compute all the interaction terms. So you have a formula with several terms. Okay, so plug these ansatz inside. It's interesting, the following fact. So what you're going to do, you're going to find first an equation for this term. You just equalize all the terms, the largest ones. Then, so you start to group your terms by orders, right? You're going to have, so this is order 0. When you plug it there, there are n squared terms. So there's going to be, the dominant term is going to be order n squared. So you're going to get something like n squared, some expression, plus n, some expression, plus some expression, plus little o1. This is basically the kind of equation you get. You divide them in chunk. Then you say, okay, I'm going to set the first 3 times 0. I have 3 functions to play with. So I'm going to set it 0, set it 0, set it 0. Okay, just playing with psi naught, psi 1, and psi 2. Plug inside and try to get 0. It's interesting what you get at the first order because it's kind of counterintuitive from what we had before. Before we look at you look at the equation and say, okay, I have Laplace equation with a drift, and so some first order term, plus, wow, this is nice term, and this is no, I mean, there is no psi here. So basically it's a second order equation, an elliptic equation with first order terms and no, let's say, still order terms. Or a right hand side. But in fact, what is the first equation? The first equation will not have a Laplacian because here, so plug this expression inside. Here there are n terms because this is the sum of the II of psi. So this is of order n. This is of order n squared because there are n squared terms, sum of E and J. So this term and this term do not interact. This is stronger than this because this has way more coefficients. So in fact, let's see if I wrote down the formula. For instance, psi naught, the equation for psi naught has no Laplacian inside. Okay, I mean, so the equation for.
Sorry, what's the difference between psi 0 and psi 1 in your expansion? I mean, there is lambda.
There is no difference at the moment. I just define that is just for convenience to have two functions. I'm just trying to find an expansion, right? So I suppose that I have a function of order, so psi naught is some smooth function of order 1, which is multiplied by 1 over n, sum that is multiplied. Then psi 1 is another function of order 1 that I multiplied by 1 over n squared, and so on. I'm trying to solve them by expansions, right? So psi naught solve the following equation. Integral, okay, of psi, so, okay, let's say I have a sum of, okay, here there is another thing I should do, but basically, let's say psi naught solve this part. I can tell you. It solves this. There is this term appearing and this term appearing. And this, if you want. But there is no Laplacian. So for psi naught, there is, so no Laplacian for psi naught since is over the n. So in fact, if you want, once you plug the expression inside, here you're gonna have the Laplacian of psi naught. So when you apply the Laplacian of psi naught, you're gonna have something like here. Psi naught second will appear here, not here. Here you're gonna have something like psi naught prime of x minus psi naught prime of y, x minus y, which is this term. For variables, right? Okay, I'm calling now the variables x and y just. So this expression in psi naught is going to appear here, but the Laplacian is going to appear here. So first you're going to solve an equation without Laplacian. And then once you solve it, you plug this as a right-hand side. So the Laplacian plays no role. It just appears always as a right-hand side in your solving. So it's curious in the sense, if you think that the Laplacian came from Monge-Ampère, that Monge-Ampère never appears. It's a lower order term in the equation. It always appears on the right-hand side to correct the next order. And okay, so now I just stated what happens. And then I'm almost done. So this is more a curiosity, but so you do this, you get several pages of terms. You simplify, you try to solve it. I mean, you have to invert the operator. It's not obvious to invert the operator. To find the solution, prove that it's smooth. It's still, it's not that you get an equation which is trivial, because it involves very obvious expressions. But so you prove that, let's see, what is the regularity is kind of weird, so I never remember the orders, but yeah. Basically what you prove, theorem, if V and W are of order CR, then psi naught is of order C, R minus 1, psi 1 is of order C, R minus 7, and psi 2 is of order C, R minus 5. That's what you get. Okay, you lose derivatives when you try to solve. It's not an elliptic equation, so it doesn't regularize. It actually loses regularity. But so you can find solutions which are smooth, at least, assuming that you have enough smoothness on the potentials. Then once you've done this, you say, okay, I have them. Then I have to solve ST dtst equal grad psi t OST. But I can plug the expression for psi t here. So this becomes grad of, I mean, I can use that expansion. So use the expansion. And then you make an answer that's also on the flow. So since the vector field decomposes sum of 3 terms, you can think that the flow decomposes as very simple structure. So in fact, you prove that ST is something like ST0, which is very simple, plus S1 over n ST1 plus 1 over n squared ST2. So in a sense, your flow that you have to solve, that your transform map at the end, is going to be a sum of 3 pieces, where this is very, very easy. This is basically trivial. It's a one-dimensional flow that you can just, it's super easy, this one. This one is slightly more difficult, but not too much. And then all the trash is here, but there is 1 over n squared in front. So that's, in fact, it gives a very good expansion. So you see, it's not really just finding a flow, it's really that you know what it is. So it's not just proving that it's smooth or whatever. We have much more. We really have a structure. So let me just conclude with a statement, a theorem, which is a statement which is usually called in the kind of in business with people doing random matrix universality. So let me state it with the right numbers. So theorem, or if you want, it's actually a corollary. Corollary of this expansion. So if V is C32 and W is C31, so that's the regularity you need to make computation. Then for every Lipschitz function of m coordinates, lip, if you do the integral of f of n lambda I plus 1 minus lambda I, n lambda I plus m minus lambda I in d p n v plus w, and you look at the same expression. So you have to put a coefficient here, alpha I, which is explicit. This is a corollary. N lambda I plus 1 minus lambda I, alpha I, n blah blah, dp and v. This is bounded by constant over the square root of n. More or less. So what do we say? We say that, okay, what happens in your eigenvalues, by the distribution they have, they're going to be usually spaced like 1 over n, one from each other. That's something that comes out of the construction. You have capital N eigenvalues, but really they are bounded. So they're going to live in an interval of finite length, and basically the space is of order 1 over n between them. So to see something, you have to rescale them, and that's why you have to put an n in front. So in this way, you see something which is non-trivial. This is the spacing of the eigenvalues. So if you take a function of the spacing of n consecutive eigenvalues, and you look what integrals you get, is exactly the same integral you get for the original one, up to a dilation factor, alpha I, which is explicit, it comes from the transport, in fact. So there is a number that you just have to prove to say that there is a dilation coefficient. But besides a dilation coefficient, basically, your eigenvalues behaves exactly the same way. So the spacing that you get here is the same spacing that you get here for the two distribution, no matter what is V or W. So this is what is called universality. The spacing of the distribution eigenvalues behaves exactly the same, no matter what is the potential. So this is the theorem, and okay, well, I stop here. Thanks.
Any questions or comments?
Yeah.
So you don't show that psi t as n goes to infinity has this expansion. You just take it as ansatz and you prove it things for this.
Right.
Okay.
Yeah, I don't care that this is true or not. I just say, I assume that it has this form, I plug it in, and that's enough to do my computation. So let's say the fact that it's true is maybe a posteriori in the sense that if it was a completely fake ansatz, probably I couldn't prove my theorem. But just that you guess the formula, you plug it in, and you get what you need. So let me mention, okay, these kind of results are known for these kind of problems, in the sense that there have been a sequence of papers by H.T. Yao and this guy is from Harvard, proving exactly all the statistical properties of eigenvalues. Sorry, actually I forgot the co-authors. Maybe I should have. That's very bad. Okay, this is a joint work, Beckerman, myself, and Ione. So these are known. Although I can tell you, like, usually a proof of like this takes 90 pages in their papers, and our take maybe 28 pages. So it's, in a sense, it's more elementary. You just, once you have the idea that you want to use transport, it's basically a computation. The advantage of this is that it's pretty robust. So in particular, now we are doing, we are extending the same kind of result, in fact. When it's not just the distribution of eigenvalues of one matrix, but the distribution of eigenvalues of multiple matrices at the same time. So in a sense, you have a distribution of eigenvalues, but the matrices can interact. So you have a potential which makes matrices interacting, so they're not independent, the matrices, the laws. And this interaction, you assume that the interaction is sufficiently small. So if they were completely independent, is this problem. Then you take a small interaction between two matrices, and this approach still works to prove these universality properties. And for instance, this was completely open. I mean, like, there are no results, to my knowledge, using probabilistic method to prove anything when you have started to make matrices interact. Well, this method works also for that setting. So, okay, that's something still work in progress. I mean, we're finishing writing up, but it's kind of monstrous to do that. So that was just a comment. Yeah.
Perhaps say a little bit about why that solver is important, but you said that, right? That it's important to get
this.
size. Yeah.
Okay, it's not important for this theorem itself, the square root of n. Okay, it's true and it's not. Here is not too important at this state. It is important because then you start to look at, so there are several experiments about universality that you can look. And there is in particular one, now I have to remember the statement, which is about, you start to look at the sum of the length of the spacing of eigenvalues. And what you can prove in the Gaussian case, for instance, is that a certain law converge to a Poisson process. So in some sense, you have kind of several quantities which involve eigenvalues that have very natural limits as n goes to infinity. And very often, these have to be renormalized suitably. So here we have n, the renormalization factor. So anything which was above n works. So here, you see, there is an n and a square root of n. So basically, our theorem is a good approximation up to, so what we get is some error is n 3 over 2. That's kind of the order we have. That's why we can get square root of n here. So we needed something above n. Now, there are other normalizations which requires to multiply by n 4 over 3, for instance. And so since n 3 over 2 is bigger, that's still good to get this one. So I'm just saying that it's good that it's not 1/2 which is crucial, it's really that we are above n in some setting and n 4 over 3 to be able to get these results. It may be possible, although it would be kind of delicate, but maybe it's possible, to, at least in this setting, one matrix, to try to do an expansion at higher order. We stopped at order 2. One could go on with the numbers. So one could try. It's not going to be me. It's already a mess, but it may be possible that one try to get a higher order eigenvalues, and then one could get even more universality property, which are known by other means. So we only get some of them, but at least some non-trivials.
Anything else? If not, let's thank the lesson again.